want to welcome our guest, Katie Mack. Come in. Yes, please do. Come on into the room, Katie. Katie has just recently written a book called The End of Everything, Astronomically Speaking. So we are, in keeping with our cheery Armageddon themes from the first half of the show, we're going to just talk a little bit further about not just the end of the dinosaurs or the end of humans on Earth, but the end of truly everything. So with us, we have a wonderful expert, cosmologist and Professor Katie Mack from NC State. Katie actually had an early passion for astronomy growing up here in Los Angeles and came to Griffith Observatory as a young girl and young woman, and went to Caltech. So very local, and but she is now, well, actually, she's right now in Toronto. I think, Katie, you said you kind of got stuck there. You were in Toronto, and then suddenly you weren't going to go anywhere.
I was in Waterloo, Ontario, just a little ways outside of Toronto, at the Perimeter Institute for Theoretical Physics, where I was doing a 6-month fellowship. But now I'm actually in Massachusetts for complicated reasons. So I had to leave Canada because my visa was up, and it's been a strange time. But I'm just doing my work remotely as a theorist. That's very easy to do. So. Now I'm in Massachusetts doing the same thing,
And we noticed the blackboard behind you. You want to what's that all about?
Yeah, so that was a gift from Perimeter Institute. I used it first for a public lecture I did with them, one of these online public lectures, and they wanted me to be able to draw stuff during the talk, and it turns out it's really useful for supervising students. So I have a research student I've been working with remotely during the summer, and I write my equations on there and talk to her, and it works much better than any kind of complicated technical annotate screen solution. So it's a very helpful thing to have.
It's like Battlestar Galactica, right? Use the lowest tech.
Yeah.
But it's very reliable. I understand.
It is.
So what drew you into astronomy here in Los Angeles when you can't really see the sky?
Yeah. So a lot of my colleagues in astrophysics, they got into it through stargazing, through falling in love with the night sky, and in LA that's difficult. I did go to the observatory a lot. My mom used to take me up to Griffith Park from time to time when there was a comet or an eclipse or something like that. And I did join the LA Astronomical Society at some point, and went to the dark sky star parties when I could. But mostly I got into astrophysics through the physics side, through trying to understand what I could about the universe, getting excited about black holes and the Big Bang and space-time and all of that kind of thing. I used to go to public lectures and read books by Stephen Hawking, and I really fell in love with that, all that mind-bendy physics.
So with all that mind-bendy immensity out there, what made you decide to talk about the end of it all?
Well, I've been doing cosmology for a while, and studying a number of different things, including early universe physics and dark matter, and a lot of times when I'd give public talks, I would talk about kind of what we're learning about the evolution of the cosmos and stuff. And at some point, I started to include some things about the end of the universe in the talks I was giving, and I was hearing some really interesting new research around certain end of the universe scenarios, and I would include that as well. And people really got excited about the end of the universe, and that was always a big kind of crowd pleasing thing to discuss. And so I thought, if I'm going to write a book, there are a lot of books out there about the beginning and not that many about the end, and it seemed like a nice way to introduce people to some cool cosmology topics, and to help people get an idea of where things stand in cosmology, and what we're thinking about in physics around that question. Because the ways we think about the end of the universe have changed a lot in the last few decades, and I wanted to help, give people some access to that information. And it was just, it's kind of a fun, slightly scary topic, and people enjoy that sort of thing. So.
Well, why don't you tell us a little bit about the book and tell us a little bit about the ways in which all of it may end?
Yeah. So the book is, it goes through 5 different possibilities for the end of the universe. And they're not necessarily the only things that could happen, but they're the ones that are kind of the most discussed in the literature, the most likely based on, or not necessarily likely, but the most seriously talked about by professional cosmologists. And they represent a range of possibilities that kind of illustrate where things could go if the data look just a little bit different, or if the theory is tweaked just a little bit. So it's a nice kind of overview of some fun possibilities. And so in the book, I start with, an introduction to just the field in general, and then I go through the Big Bang to now to get everybody on the same page, and then I go through destroying the universe for several chapters, and then talk about how we're figuring it out and what kinds of tools, new telescopes and experiments and advances in theory we're going to have in the next few years and decades. And then I have a little epilogue that's kind of like, okay, we've been through some stuff. Let's talk about how we feel about this, and I include a bunch of quotes and discussions with other cosmologists, because when I was researching the book, I was going around talking to colleagues about, where they think the field is going and such. And I made sure to always ask the question, so how does the end of the universe make you feel? And I got a lot of different answers. And so that was really fun and interesting to hear how people who are actually studying this day to day feel about the prospect of the universe coming to an end. And it wasn't all the same response. There were some people were totally fine with it, some people not at all, and that was very interesting to see.
Great. Well, do you have? I understand you have prepared a few visuals to help share some a little more in depth with this.
Yeah, so I thought I would go through 4 of the 5 scenarios just briefly to give a kind of overview of what these things kind of look like. And then, I won't go into any detail on these, but just to give an impression of kind of where things stand. So I'm going to try sharing my screen, see how this goes. Let's see. Okay. All right, so hopefully you can see my screen there, my title slide. Okay. All right, so yeah, so this is just a sort of brief talk about how the universe ends, a few different possibilities for that. So, okay, so the main idea here is to think about the cosmos as a whole and where things might go in the future, what we can expect to happen, and is it really just going to kind of dissipate and go away and be destroyed completely, or what should we really look for? So in this case, the 4 that I talk about are the Big Crunch, heat death, the Big Rip, and vacuum decay. Now in the book, there's an extra one, a bouncing cosmology, and we can talk about that more later. But for the purpose of this, you get the first 4. So starting with the Big Crunch. Okay. We are here. We're in the Milky Way galaxy. This is a nice view of the Milky Way galaxy from the southern hemisphere, where you can see the center of it, which is very cool. And if we were to be outside of our galaxy, it would look something like this. We're kind of on the edge, somewhere near the edge of this spiral galaxy. And our galaxy has somewhere around hundreds of billions of stars in it. And we see galaxies all across the universe, and we can see them out to extreme distances. And when we look out into the distance and into the past, we can see galaxies that existed during the first few billion years of the universe. And we can see that what we see when we look out into the cosmos is that galaxies are moving away from each other. They're moving away from us, so we see them as though they're moving away from us, but they're really every sort of well-separated galaxy is moving away from every other. The universe is expanding. And so for a long time, there was this question, will the universe continue expanding forever? This expansion that was sort of kicked off by the Big Bang, Or will the gravity of all the things in the universe start putting the brakes on that expansion, pulling things back and causing it to recollapse? And so if that were to happen, what we would see is that the galaxies would start coming back together. This is my very sophisticated animation of this. And we would start to see that instead of galaxies all receding from us, they would be approaching. And so we would see them getting closer and closer, and the universe would be getting denser and denser. And at that point, we would see more interactions between galaxies. And no, we do see that a lot in the sky now. There are places where galaxies are colliding with each other, interacting. It gets very complicated. But that's not really what is dangerous about a big crunch cosmology. So it's not that galaxies smash into each other and everything kind of breaks apart like a car crash. The thing that's dangerous about a big crunch, about the universe contracting, the thing that really kills the stars, is that when the space is compressing and all of the galaxies are coming together, it's not just the matter that's compressing, it's also the radiation. It's all of the light, the background light that's been in the universe all this time, and also the starlight that's been shining for all of these billions of years. And so if you are a star hanging out in the universe when the big crunch is coming, the thing that kills the stars, and this is the coolest thing about the big crunch, so I'm giving a little bit away, but you might appreciate it. The thing that kills the stars during the big crunch is not the stars crashing into each other. It's the fact that the ambient temperature of empty space, the amount of radiation that is being compressed into a smaller space during the big crunch, it gets to a point where it's enough to ignite the surfaces of stars and cause thermonuclear explosions all across the surfaces of stars. And that's what kills the stars. And I think that's fantastic. And of course, at that point, nothing survives. So it's a kind of scary story. That bit was first worked out in the late 1960s, and was a very scary thought. That at that time, that seemed to be the way things were going, that we were going to head for a big crunch. And now we don't think that's going to happen. More likely is the heat death. And this is the one that is thought to be, probably what's going to happen to our universe. So the heat death starts the same way as the big crunch. The universe is expanding, but instead of the expansion stopping and turning around, it continues. And in fact, now we know not only is the expansion continuing from the sort of initial kick of the Big Bang, but it's also accelerating in its expansion. The expansion of the universe is speeding up. And we don't know exactly why that is. There's whatever's doing that, we call it dark energy. It's making the universe expand faster. It might be a cosmological constant, which is a sort of just a property of space, that space has this inherent expansion in it. And if that's the case, then over time, there's more space, and so there's more expansion of space, and the matter that should be sort of putting on the brakes on this expansion gets more and more diluted, and so the expansion just keeps accelerating and accelerating. And what that does is that it just increases the empty space, and everything gets more and more isolated. And in this scenario, by around 100 billion years from now, our little group of galaxies will be totally isolated from the rest of the universe. We will not be able to see distant galaxies anymore. And each galaxy, or little group of galaxies, if they're already kind of in a clump to begin with, will be more and more isolated, and there won't be these grand galaxy collisions that could bring in new gas and form new stars and everything. And so the stars that exist in each of these galaxies will kind of burn out and fade away, and matter will decay and black holes will evaporate. And over time, the universe ends in this cold, dark, quiet, empty space. And that's called the heat death of the universe, when there's really nothing left in the universe except a little bit of trace waste heat from all of the processes that ever occurred in the cosmos. So that's a bit of a sad story, and not a particularly exciting one. The next one's a lot more exciting, and we can't entirely rule it out. So the next one starts the same way as the heat death. The universe is expanding. It's speeding up in its expansion because of dark energy. But there's an extra piece of this picture in the scenario of the Big Rip, because in the case of the heat death and our sort of usual idea of the accelerated expansion of the universe, the dark energy is able to pull galaxies away from each other because there's a lot of empty space, and anything that's not sort of already bound can be separated because there's more empty space in between. But if dark energy is just this cosmological constant, just this property of space, it doesn't affect the galaxies themselves. It doesn't like try and unravel those things. If there's already a gravitationally bound object like a galaxy or a solar system, it's fine in that picture. But the Big Rip is what would happen if dark energy were something more violent, if dark energy were something that kind of got more powerful over time. And then not only was it able to move galaxies apart, but also to kind of pull the stars away from galaxies, to pull planets away from their stars, to pull apart eventually all of matter itself. And that would destroy not only all the structure in the universe, but at some point kind of tear apart space completely. That little animation there that I just did, I did that in Keynote, but a few years ago, NASA made an animation of this to illustrate the idea of the Big Rip, because depending on how you look at the data, certain bits of the data might prefer this a little bit over other possibilities. And I just want to show the NASA animation here because I think it's really great. So here we go. The expansion begins, and then, oh no, the galaxies are torn apart. Oh, yeah, I gotta watch that again. So the thing about the Big Rip is we can't necessarily say that it won't happen, because the difference between the kind of dark energy that gives you a heat death and the kind that gives you a Big Rip, it could be very subtle. So there's a measurement you can do having to do with what the dark energy is, and if you get a certain number on that, then you've got cosmological constant. If you get a number that's any little bit smaller than that, then you get a Big Rip. And so all we can really do is say, we have at least about 200 billion years before it's remotely possible for a Big Rip to happen. So that's where we stand with that. Although if you ask the theorists, sort of me, but also other theorists, the Big Rip is it's sort of a less appealing idea in terms of the theory. Which brings us to the final one I'll talk about today, vacuum decay. So this is my personal favorite because it combines some cool ideas in particle physics with universe-ending cosmology in a really fun and interesting way. So a few years ago, the Large Hadron Collider was able to find kind of the final piece of the standard model of particle physics by discovering the Higgs boson. So this is a picture of an animation of a cartoon of an event display at the Large Hadron Collider. This is a machine that swirls protons around in an accelerator and smashes them together to see what comes out. And the point of doing that experiment is to examine the forces of nature, the fundamental particles that make up everything. And when the Large Hadron Collider turned on or found the Higgs boson, it completed the standard model of particle physics. So this is an illustration of the standard model of particle physics with the Higgs boson up there. And what we have here we have the quarks, which are particles that make up the centers of atoms, protons and neutrons. You get 3 quarks each in protons and neutrons, and the other quarks are just related particles. There's the leptons, which include the neutrinos, which go through, they're produced in the sun and they go through the earth all the time. There's the electron and its cousins, the muon and tau particles, the electron being what goes around the nucleus of atoms, or if you're looking at it in a quantum mechanical way, it's a kind of haze of electronness probability ball around the centers of atoms. And then on the right on this picture, we have the gauge bosons, which are the force carriers, the things that that mediate the forces of nature. So there's the photon that does electromagnetism and light and magnetism and electricity, the gluon that holds particles together inside the centers of atoms, and the gluon does the strong force, the strong nuclear force, and then the W and Z gauge bosons, which are they have to do with nuclear like radioactive decay and things like that. They mediate the weak nuclear force. The point of showing this is that these are the particles we know about. This is the standard model of particle physics. It matches all the data we've ever gathered in particle experiments to a pretty good precision. There are a couple places where there might be little anomalies. At some point we had to revise the mass of the neutrinos from 0 to a little bit more than 0. Basically, the standard model of particle physics works, and one of the things that it can tell us is it can tell us something about how stable physics is, how stable the universe is. Like, is this sort of configuration of particles and fields, does this really work in the long term, or is there something slightly off about it where it could collapse into a totally different configuration of particle fields that would be bad? So you can take a few of these particles, the top quark and the Higgs boson, and you can do some measurements around those, and you can make a plot of regions of stability or instability or metastability. I'll explain that in a minute. For like the universe, for how physics works, where in this plot, the mass of the Higgs boson is on the x-axis, the mass of the top quark is on the y-axis. And so, for example, if the Higgs boson had a mass of 50 GeV and the top quark had a mass of 50 GeV, then you'd be in this nice stable region where everything's fine, and the universe and physics work fine forever, and you're good. So finding the Higgs boson and measuring its mass gave us important information about where we sit in this parameter space, what our universe is really like, right? And when that measurement was done, we found that we live right there. So that's the metastable part of the plot, which means that the universe is stable for now. And specifically, it means that there's a kind of vulnerability built into how physics works in this universe, where something could happen that could change the laws of physics at one point in the universe and create a catastrophic cascade of a different kind of space. I'll show you what this looks like. So what would happen is we have this Higgs field, which is this sort of energy field that pervades all of space. And at one point somewhere in the universe, that Higgs field would undergo a quantum transition where it would change its value, which would totally restructure all of physics and create a bubble of a different kind of space, where inside this space, the laws of physics are different. The standard model is not the standard model anymore. You have different particles, different fields. And if you were in that space, the constants in nature would be different. Your particles wouldn't hold together anymore. That would be bad. And this bubble, it's called a true vacuum bubble. This bubble would be expanding out at the speed of light, which means that if you're standing nearby, then you will not be able to see it coming. There is no possible way you will know that this is approaching you as it's occurring. And what it would do to you is it would first, the bubble wall would come and sort of incinerate you, and then you would be inside this bubble where your atoms wouldn't hold together. And then it turns out after that, you would collapse into a black hole. So clearly that's
death. We all becoming black holes. That's kind of dramatic.
Yeah. So clearly this is something we want to avoid. And there are a couple of things I always say about this. One is that because this is a quantum tunneling event, we can't predict when or if or where it would happen. All we can say is that there's, the probability is that it almost certainly would not happen for the next, 10 to the power of 100 years or something like that in our observable universe. On the other hand, we can't say for certain, but there are a number of reasons we shouldn't worry about it. One is that, there's nothing you could do about it. You wouldn't see it coming. It would be totally painless. because it's happening about the speed of light and your nerve impulses don't travel that fast. Nobody would miss you. There's no tragic aftermath. But also, the idea that this can happen at all is based on the standard model of particle physics being completely reliable. And we know that it's not. So if we look at what the universe is made of, we know that the universe is made mostly of dark energy, which is the stuff I mentioned before, where we don't know what it is. We don't know how it's going to act in the future. It's made, after that, most of the rest of it is dark matter, which is some invisible matter that holds galaxies together, but we don't know what it's made of. It's not something where we, can say, well, it's that kind of particle there. And then there's about 5% of the universe that's all of known particle physics. The entire standard model of particle physics is in there. So if we're trying to make an inference about what the universe is going to do in the future, and we're basing it on this little tiny 5% slice when there's 95% of the universe that we do not understand, we're bound to be missing something. So in my work and in the work of other cosmologists, we're putting a lot of energy into trying to understand that 95% of the universe, that's the invisible, mysterious stuff that's driving the evolution of the cosmos. And maybe once we figure that out, we will find entirely new fates for the universe, entirely new ways that our whole universe could evolve and change and potentially, come to an end. So that's the end of my presentation. So I will turn this off.
Before you turn that off, oh well.
Yes.
Yeah, well, you're still there. Could you go back to the slide with the mass of the top quark and the mass of the Higgs boson?
Yeah.
Before you put the dot up there, I was thinking to myself, okay, what does it need to be where any of the four possibilities could be true? And lo and behold, that's the mass of the top quark. I mean,
it is weird that we're right there.
Yeah.
Yeah.
Really, we didn't know Higgs boson, any of those were possible until, was it 2012 or whenever that was?
Well, I mean, we couldn't have been, if we were in the instability part, our universe would already be dead. So that part was basically ruled out. But yeah, I mean, it was kind of assumed we'd be in the stability region before this was discovered. And if you talk to particle physicists, some will say like it's weird enough that we're right on that edge, that we're just barely not in the stable region, that this must be telling us something profound, that we can't really be metastable, that there's the idea that the universe really is in this state where where the expected lifetime of the universe is more than the age of the universe, but not so much more. That seems suspicious, right?
And the critical density, the ratio of the observed density to critical density is so close to 1 that it must be, I mean, it just has to be because it's so close. And it sort of has that same feel. You're right on that border. And
I mean, yeah, if you zoom in a bit, we're not that close to stable. It's but it's a fairly small part of the parameter space that we're in. So it does seem like we're like, it's only, you don't have to be that wrong on the measurements to make us actually stable. So maybe it's telling us something deep that that there's some small correction factor that we haven't figured out yet. And if you talk to different physicists, you'll get different answers. I was talking to one last summer who was saying like, well, maybe we've just been lucky so far. Maybe we don't know what the real time scale is on this transition. Most people would say that it's the time scale is so long, it's not something that's going to be a factor for how the universe evolves. But particle physicists are taking this seriously. I wrote a paper about this stuff because I find it fascinating. It's a real topic of research, and it's a really interesting possibility that the universe, just might not be fully stable. There's some other state of the configuration of physics that is preferable in some way. And if you tweak our universe in just the right way, we will revert to that unlivable space.
That's remarkable. Why don't you come on back in the room, shut down the sharing so we all have a bunch of questions. I know one I want to ask right off the bat is, and it ties to this question about the measurements. being so close. I mean, do we really know the mass of the Higgs boson that well, or could we
Yeah.
be? So I do want to ask the theorist some observational questions, but you
Sure.
mentioned that as a critical measure. You also mentioned a measurement of the dark matter as being a critical. If it's low enough, then you are in the big
Dark
rip.
energy.
Oh,
Yeah.
pardon me, the
dark energy.
So tell me about these measurements. Are they on the horizon? Are we going to get answers to that? Any refinements?
Yeah.
How are we going to know?
Okay, so with dark energy is a really tough thing to study because all it really does, as far as we can tell, is make the universe expand faster. It seems to be totally uniform through space. It seems to be acting the same, through time, as far as we can tell. We haven't found anything different about that. It's invisible. We can't touch it. Experiments don't seem to be able to do anything to it. So what we can do is we can measure the expansion rate of the universe at earlier times than today. We can see how the universe has been expanding, the expansion history. And we can measure how galaxies and clusters of galaxies and so on have formed throughout history, because that's been influenced by how the universe is expanding. So those are the kind of the measurements we can do. And so far, all of those measurements are consistent with the idea that dark energy is just a cosmological constant. It's just something that is a property of space. And the reason the universe is speeding up now when it wasn't speeding up before, so the universe was slowing down in its expansion for about 9 billion years, and it just started speeding up in its expansion about 5 billion years ago. The reason that's happening is because there's some constant amount of dark energy, constant amount of cosmological constant. The density of this stuff, whatever it is totally constant. And that means that in the early universe, when the density of everything else was really high, then the gravity of those things was able to slow down the expansion. But once the expansion got big enough, the density of everything else was going down, and then the gravity was no longer strong enough to slow down the expansion. And then the dark energy took over and made the expansion go faster. And that, so far, everything we've seen is consistent with that picture. But there's a measurement we're trying to make. We're making a measurement of what's called the equation of state parameter of dark energy, which is measuring. It's a measurement. It has to do with the pressure and the density of whatever this stuff is. And that number, if that number is exactly -1, then we have a cosmological constant, and we know exactly what the evolution of the cosmos is going to be. If that number is anything at all less than -1, then that's the kind of dark energy that leads to a big rip. And so the problem is, if we're trying to measure that number and we are just continually zeroing in on -1, we're never going to have it so precise that we can completely rule out any other number, right? Like that we completely rule out something that's not exactly -1, right? There's always going to be some error bar around there. But we can measure that number, and we can measure if that number changes over time. And so far, it seems like that number has not been changing over time, and it does look a lot like -1. But we're getting more data. There are a couple of cool new observations that are going to be happening. There's the James Webb Space Telescope that's going to look at some very distant galaxies, and there's the Vera Rubin Observatory that'll carry out the LSST survey. I don't remember what there's a survey that the instrument used to be called LSST. Now the survey is called LSST, and the instrument is called the Vera Rubin Observatory. But what it's going to do is it's going to measure millions of galaxies across the universe and map out the universe with extreme precision, and that will give us way more information about dark energy and how the universe has been evolving and will continue to evolve, presumably. So there's those things, and then there's also, theoretical work around things like maybe if you modify gravity, it'll change some of these pictures, and so we can do tests of gravity and tests of general relativity, Einstein's theory of gravity, and see if tweaks to that will give you a different answer for how dark energy is working. And maybe dark energy can be something different that changes over time in some interesting way. So there are lots of measurements around that. And then there's just advances in theory and maybe we'll find some cool new ideas for dark energy in the theory space, because there's still some major theoretical problems with the cosmological constant. It's an idea that's been around since Einstein, but it doesn't play well with quantum mechanics in complicated ways, and so maybe we'll find some better solution for that as well.
I meant to say at the beginning, and so I'll say this now, that I imagine that some of the people watching may have questions for Katie. And so the way we're handling questions for you people out there is that you type it into the chat on the YouTube channel. And we have, as you know, folks who are monitoring the chat, and they can bring your question into the room. Oh, looks like we have one.
Well, just a point of clarification that's requested from the chat. So when we were looking at that graph of metastability, that point, what exactly is that point? Is that us where we are? Is that the universe as a whole? Some people in the chat were wondering if you could clarify that a bit.
Yeah, so what that is that point is, it represents the value of the Higgs boson mass and the top quark mass, and those are parameters that fit into our mathematical model of how particle physics works in our universe. And so it's really a question of, I mean, it's often, we talk about it as the stability of the universe, but it's really the stability of how particle physics works in our universe. So if we were at a different point in that graph, then you would have different relationships between the particles and the fields and so on. And those would be more or less stable in the sense that, so the thing that's unstable is that if you kind of increase the energy in the Higgs field, you can kind of change its value in a certain way, and it's complicated to go through this. So the laws of physics are okay. Well, the laws of physics are energy dependent. Which is why if you smash particles together at higher and higher energies, higher and higher speeds, you get different answers and in interesting ways. That's why we need huge particle detectors or particle colliders to crank up the energy to see what the laws of physics look like at higher energies. And basically, this instability thing is a statement that at high enough energies, the laws of physics break in such a way that you really don't want them to. And it's not because you can actually reach those energies in space. Like, particle collisions in space or something can actually reach the energies that would give you a different answer in terms of like change the laws of physics in this unfortunate way. But quantum tunneling events can kind of randomly take you to these parts of these different parts of the sort of abstract mathematical model space of the physics, and change the laws of physics locally in a way that would propagate out in a bubble. So unfortunately, it is a little bit technical. I do my best with analogies in the book
I think you did a good job. That explained it to me. We do, and then we have another question. This one's a bit more of a fun one, but Janelle asks, which of these universe ends, if you had to see one in a science fiction story, which one would you like to see happen in a science fiction story the most?
In a science fiction story, so I think that the problem with the Big Crunch is I think that would just be a horror story. I don't think that would be science fiction. I think that would just be, I find that one the most terrifying and like horrible, because you would see like the universe, you'd be being cooked, you'd see it coming, and it would be very upsetting. So I don't like that one. The vacuum decay is too quick. You don't like, I've thought about trying to write that into a story myself, because I thought it'd be fun, and it's just like you don't even notice it, right? Like it happens at the speed of light. You don't notice it happened. There's no dramatic tension, like nothing. It's just
a very short story. One day you're there.
Yeah. You wouldn't even know it got you. So that's no good. And the heat death has been done in various pieces of literature, but it's a little bit sad. So I think you have to go with either the Big Rip or the bouncing cosmologies, which I also talk about in the book. The Big Rip would be interesting because you would get to see the Milky Way like sort of drifting away, and you would get to see the outer planets spiraling out into the void, and then it's only like something like an hour before the whole universe is destroyed that like the Earth blows up. So it gets more and more dramatic as you get closer to the end, and that would be kind of interesting in a science fiction story. And then the bouncing cosmologies could also be quite interesting, because there are kind of possibilities of like sending information through. And I actually have read a science fiction story about one of the bouncing cosmology scenarios, and I talk about that in the book. Actually, I have a shout out to that story because it is kind of cool. So.
Well, this is a good moment since you mentioned the book. And David, I was going to come to you in a sec, but no, stick around, Brennan, because there are more, I'm sure. And so because we want Katie to sell some books, I wanted to have people buying her book and reading it. So here's the book again, and you can get it on your lovely, no brick and mortar store online. But even better, if you live here in Los Angeles, you can go to Skylight Books. Because I believe, Katie, you sent some nameplates, some signatures.
Yeah. So I have these little signature cards, book plates, and I sent a pile of them to Skylight Books, and so you can get. So I didn't physically sign the book. Signing books during a pandemic is difficult, but you can get a sticker that I signed stuck into the book. And it's close as you're going to get to a signed book at the moment.
Perfect COVID solution to a book sign. Send the nameplates, and so she's not in person at Skylight Books, but also for those of you who know, here in Los Angeles, Skylight Books is right in our own local Los Feliz neighborhood, just below Griffith Observatory. You literally can look up from Skylight Books and see us. So we encourage you to, do the in-person thing, get one that's signed. And you
can probably do a curbside pickup or something like that, and do it in a very responsible way.
Phyllis is doing very well, and so come and enjoy a nice leisurely stroll past the bookstore. So David, I know you said earlier you had some questions. Did you want to ask?
Well, one of the questions came from Twitter earlier, and you answered the particle death one wouldn't hurt because we wouldn't see it coming, we'd just die. But would the big rip hurt? Would that one hurt? Because you said there would only be an hour between.
Yeah, I think, unfortunately, I think it would. So the problem with the big rip one, here's what you do if you want to survive as long as possible during the big rip. You don't want to be on the Earth, because the Earth is going to be ripped apart. Like basically the larger the thing is, the earlier it's broken apart by the force of the dark energy. So you want to get into the smallest space possible. You don't want to be dependent on the Earth. So you want to get a little tiny spacecraft, or maybe just like a space suit, and be out there away from things, have a very small amount of space, within your little region, because it's the dark energy in the space that's going to get you, right? And you can watch the Earth get ripped apart, and then very shortly after that you die. And because it's I think it might hurt. I don't know. I don't know what happens to you if it's dark energy that's doing this. Maybe it's I don't know. Maybe you don't feel it quite the same way because it's just the space is actually getting bigger. And I don't know. But
so what you're saying is have one more glass of wine as you watch the Earth get ripped apart, so you fall asleep and you don't feel a thing.
Sure. Yeah.
It's a little tough through your visor on your space suit.
Yeah.
And did you have other questions, David? Just because I have.
Well, most of them were answered. I was curious about which of these you would prefer to see. The science fiction question kind of answered that one. Do you have a feeling of which of these is actually true? Just sort of a gut feeling on it. I know as scientists we don't go on that at all, but which do you personally think is going to happen?
Well, so I think, the heat death is the one that's, I think, taken most seriously within cosmology, because it's sort of the simplest model in a lot of ways. You don't need to introduce some new thing. It's just, it's cosmological constant, and it's the evolution that we see happening now. But if you talk to particle physicists, they talk a lot more about vacuum decay, while at the same time acknowledging that we don't know for sure it could happen, because maybe sorry, I'm distracted by your cat. Yeah, so we acknowledge that we don't know for sure if vacuum decay could happen because maybe things change at different energies. But if vacuum decay were possible, it would happen before the heat death was complete. So that would be the one that would happen first. But I mean the heat death seems to be more likely.
Yeah, with vacuum decay, is that the sort of thing that a mad scientist could create in a lab and kill us all?
No. I mean, so there have been a few papers written about how hard that would be, actually. So, like, it's not clear that there is a physical way to do it on purpose. That's still slightly an open question. Certainly not with any kind of technology humans have any sort of access to, but maybe not with any technology even conceivably possible.
I want to ask a question, Brendan. Are there any from the web? Because I have one, and then if you want to come back, or just keep watching, and I have a question for you, Katie.
Yeah, I'm coming through. I'm gonna hop out of the video part of it while I keep looking for stuff with the other moderators.
So we won't keep you all night because let's remind everyone that Katie's on the East Coast, so it's getting past 12:30 at night for her. But I was struck very much, and in fact, I was thinking about this when I was looking at the book. And you said part of the reason you wrote it was that things have changed so much recently. And one of the things that struck me in the book was that you said not everybody agrees on what the end will be, but everybody agrees there will be an end. Where when I first went to grad school, steady state was still something people talked about. It was largely gone, but that was still considered a viable debate within within astronomical research circles. And I was in grad school before the Kobe result came out. So, there were still people wanting to say that the cosmic microwave background radiation was not the thermal remnant from the Big Bang. So, I guess I'm more than anything, I'm saying my age, but my point is it's a big shift. I mean, the resistance to moving away from steady state into a Big Bang cosmology, was so deeply ingrained from cultural ties, religious beliefs. People did not want to give up the steady state, and now steady state isn't in the picture. So I'm curious about, sort of what you think that means for society. What are the spiritual isn't quite the right word, but it's more like psychological, psycho-spiritual level of the difference between a universe that goes on forever and a universe that definitely ends.
Well, it's interesting. Since writing this book and since talking a lot about these ideas, I've heard a lot from religious people from a number of different traditions, and a lot of times the message they have for me is, my religious tradition predicts exactly what you're talking about. So although although the steady state idea, the idea that the universe is just gonna, has been here forever and is going to stay the same forever, is appealing in a certain to certain kinds of religious thinking. It's also maybe appealing the idea that there was, somebody started everything off, and so I know that a lot of people will say, oh, I don't think the Big Bang is inconsistent with my theology because, okay, maybe God that did that, and that's definitely something that a lot of people are comfortable with. So I don't know. I mean, I still do also encounter resistance, not among astronomers or physicists, but among members of the public who say that it's silly to say that the universe could end. And a lot of times they, they bring up like, oh, well, you can't create or destroy energy, and therefore the universe has been around forever and will be around forever. And these kinds of ideas that are, not necessarily true in the way that they think they're true, but ideas that are sort of comforting that nothing can be created or destroyed. It's just changing form, and I think that's an idea that's quite appealing to a lot of people. Like, it's just changing form, and people even talk about that as a way of talking about an afterlife too. So, and I think that's not how we in physics talk about these things. It is true that energy changes form in a lot of situations, but on a cosmic scale, saying that nothing can be created or destroyed is not it's not a principle that we hold dear or that we think is necessarily valid. So, but culturally, I see why that's appealing. So I think it's there's kind of a mixed response to the idea that the universe is vulnerable to destruction, and that it has been evolving over time. But the idea that it's changing is certainly more accepted now, and I do think that's interesting that we're like, okay, I guess the universe does change, it has evolved, and but maybe there's still a way around it, and within physics there doesn't seem to be, but culturally it's just a mixed bag.
Yeah. Well, oh,
I do have one more quick question. This one's actually from one of our moderators. They're asking, you were talking about, you've interviewed people and asked them what they feel about when you talk about the end of the universe. How do you feel about the end of the universe? In brief, of course, not
Sure. Yeah. So when I was writing the book, and I was writing about how everybody else is responding to this question, my one of the pieces of feedback from my editor was like, oh, you should really put in a lot more of your own response. And I was like, I just don't know. Like, I'm struggling with this. I don't know what I think. And I don't, in the book, I have a little bit of, maybe I come to a little bit of a conclusion, but I'm still not entirely sure how I feel about it. I think I'm more at peace with the idea than I was when I started writing the book. But I still do find it kind of difficult to grapple with the idea that the universe doesn't go on forever, and that maybe, if you look into the far enough future, humanity doesn't really have a legacy. And I don't know, like that's still upsetting to me. And I'm still not sure quite how to conceptualize that. So I'm going to just hedge a little bit right now, but
of course, no, it sounds like we have to read your book to get a little bit more of a taste.
I think so, yeah.
I don't know. Personally, 2020 is making me grapple with the end of everything. So I think your book is a great title to read to kind of cope with it all. So that's my take.
I do think that it's thinking about the far future of the cosmos and thinking about kind of how we fit into this much bigger picture can be a helpful thing when daily life is overwhelming. I do think that if you're sort of feeling like trapped in your own little space, watching the world fall apart around you, thinking about this much bigger picture and the evolution of the cosmos and these giant forces and how everything fits together on this much bigger scale can be kind of a nice escape and kind of comforting, and at least for me, I find it helps me put things into perspective in a way that I appreciate.
Well, that is a nice segue to saying it's the same thing as looking at the night sky, I think. Whether you're reading about it and conceptualizing or just going out and looking at that beautiful Jupiter and Saturn and Mars that I hope you will all go out and look at. It's a wonderful calming experience to see the larger context for sure. It's late. I want to just finish by saying thank you for all of the work that you do in science communication. There has never been a more important time for, well, maybe every generation says that, but it sure seems like a pretty important time to be thinking about science and understanding what science is and how it works and how it affects society. And so I don't know if you have any comments you want to say on it. The comment I want to make is to say thank you for being such an effective communicator and for keeping people engaged with science, because it is such an important time for people to understand it.
Thank you so much. And, thank you to all of you at the Griffith Observatory and the work the observatory was hugely influential for me. And I know that it's such an amazing resource to have in the LA area. And these kinds of programs, reminding people to look at the night sky and giving some people some connection to what's going on in space, I think that's hugely valuable. So I really appreciate the work you're doing as well.
Well, thank you so much, Katie.